Using here superposition theorem, here, superposition. At the point here, no memorization here, here. What does the principle of superposition say? You have done it in circuit theory, hopefully. So you have three sources, internal resistance, three sources, E1, EMF E1, feeding EMF E2, okay, E2 volts, sorry, V2, volts, batteries, and this is feeding a resistor, say for example here, RL. You want to find what is the current that flows in the RL. So we make use of superposition. Superposition says that I pretend this one is killed. So therefore this is replaced by short circuit. So the circuit becomes like this. I'm very surprised. E1. So this one is supposed to be absent. So therefore it is replaced by R2 with a short circuit here. And then we calculate resistance RL, RL due to E1 alone. And then you do the same thing with E2. So you kill E1, short circuit, R2, E2, V2, V2, and again this is fed in RL. This is depending on the polarity, what is the atom matter polarity, I, R, L, due to E2. So depending on the direction of this and this, I add a subtract and then give you the total current. That's a principle of superposition, principle of superposition is superposition. So the principle of superposition assumes that when you find the effects of one, the other one doesn't act, it's out. And you proceed in turn. In this case, there are two of them. Okay? So in our problem here, let me take the second problem here. I have three agencies providing the fields. So the field due to this one was a positive coming out. This one doesn't help, it's going to the right, it starts from it coming out here. So it's as if those two are now absent. Then you repeat with E2 as sigma 2. When sigma 1 and sigma 3 are absent, then you proceed with sigma 3. When sigma 1 and sigma 2 are absent, and then you add or subtract depending on the direction. That's how we are doing superposition. You cannot memorize this thing. What for? A problem can be changed. You only understand, you try to grasp a concept, not a solution. How we proceed? Some people don't realize that this sigma 3 also contributes the field at point P here. All the sheet of charges contribute the field at point P, EP, they all contribute because by superposition, when you break out this one, the field coming out here. You break out the second one, sigma 2, sigma 3, you break out the first one, and the last one, find the field due sigma 2. Of course, the sigma 2 got the field. It goes right through because the others are not present. That's why. Sometimes it's called superposition, right? Go right through like this. This doesn't exist anymore because they are absent. Sigma 2, when you're looking at the effect of sigma 1, sigma 3 and sigma 1 are absent. Then when you look at the effect of sigma 3 is coming all the way to the left, passing to P, sigma 2 absent. So therefore you are adding or subtracting dependent direction. That is what is called principle of superposition, which you presumably have learned in your circuit, but you haven't. Some of you haven't grasped it. Just memorize the solution. But I know Polytechnic has got this bad habit. I have student notice there. They tell me, no need to explain. Just give them the solution. Memorize. Memorize something useful, not dance. That's what we did. Now looking at this one now, sigma 1 by itself. When I look at the contribution of sigma 1 being positive charges coming out, because the electric field comes from positive and that will always go from positive to negative. Negatives are infinity. So this one goes to the left, that goes to the right. This one got no part to play here because it starts from here and never passes to B. So when you're calculating something, you've got to know the data, you've got to know what you want. If you don't know what you want, you can't do anything. You go to the bank, you just stand there looking at a cashier, look suspicious there, mouth or closed, never say anything. You call the police, catch you. You're a hijacker, you're a robber, whatever. Unless you say what you want, they don't know what you want. They can't guess. Hey, you want the field where? At the point P here, nowhere else here for this particular case. So you do the contribution to this one, those two are blank out. Contribution to do this one, those two are blank out. Contribution to the last one, those two are blank out. That's what we are doing all the time. There are 3 terms because there are 3 sources. We know the result. And then the concept which I said that when you calculate the electric field from a system of charges, you pretend that at the point P where you want the field to be, you got to know what the point P is. You pretend you have a point charge, there is a charge of +1 unit charge down there, and then you calculate the force acting on that +1 in magnitude direction. That is a field by definition. This is what we did. Too much emphasis on memorization is a problem. Memorize, memorize, memorize. Here, this problem. Calculate the field at point P here. You can see test charge +1 here. Actually, there is no charge there. It is a concept. Pretend there is a charge of +1 there. And then you calculate the force. Because this concept is based on Coulomb's law, Q1, Q2, 4 pi epsilon r squared. The force divided by Q2 is Q1 times 1. That's what we are doing. When I find the force acting on charge +1, that's what we do all the time since we started. So I find the force acting on here, dq times 1, give me this, and then I carry on and I integrate for adding for small element. This is the field finally. So this is the force, the field, force due to the whole rod of charges on a charge of +1 or T. That's what we're finding. That's the definition of electric field. Electric field is a force acting on the unit test charge coming out from a distribution of charges. So, when you learn active learning, you sit down, you think, you concentrate what you are saying, what you want, not memorize. These days are over. These are over. You cannot memorize. You can memorize the solution, the problem changes, you are dead. A simple problem like this, unless you understand +1, I just rotate, I ask you find the field on the perpendicular bisector of this charge here. So what? The simple what? You set the coordinate system, you divide the small element, put the charge +1 there, find the force and the field. You don't learn solution, you learn the concept, how to do certain things. You learn the software to operate the machine, you think the machine will be the same all the time. And they upgrade the software, you're dead already. Right? You run a coding language. They change update, finish already, gone already. Okay? So now we just start the topic here. Oh, by the way, the tutorial given to you, solution is given to you, is very, very detailed. My own solution explain a lot of things. Why you want the field to be, why you draw the line on surface, why you draw line on surface, why, everything is given to you. So please go and study it. Active learning. Don't wait until the exam to look at it. I remember in the earlier years, I didn't provide solution until halfway to the term. Students say, oh, you never provide solution. I said, I provide solution, you don't read it. You don't even read it, you don't look at it. Now you give a solution from the beginning, some of them have to look at it. And then, so what's the point? Excuses everywhere. Okay, so this one is a bit of history for you to learn about magnets. The new topic. So what will happen is that they used to have, they think that magnetism always comes from magnet at first. Until Ampere did some experiment, you find passing current through a wire, you find that compatibility is detected. So there is something there like magnetic field. So you can read yourself about some history. So as I said before, the concept of a field is influenced, for example, of charges. At the given point as charge, there's a force acting on the charge. And you define this as a field. You sit near somebody who's been running, there's a field of heat and smell around the person. So this, you can't see it, but you can feel it, you can measure from the senses. So similarly, the magnetic field will be seen very soon now. For the effect it causes, for example, the concept of electric field, okay, is the force acting on the unit test charge. The test charge always one test charge. Field. A force acting on unit test charge. I've been yelling all these weeks. Force acting on unit test charge represents the electric field. This is a picture. This is the definition coming out from the law of Coulomb. Let me explain to you how we get the 1, Q1, Q2, 4 pi epsilon R squared, the force between the charges Q1 and Q2. I divide left hand side by Q2, I have Q1 times 1 over 4 pi epsilon R squared. It means that the force acting on 1. So we use this convenient concept to calculate the field at a given point P. So at a given point P, what the field there, you put a charge of +1 there, calculate the force, that's the field. And the charge of +1 is as if it is a sensor, a small sensor, the field. Okay. But actually there is no charge down there. There is no charge down there. One girl asked me just now, it was confusing. There's charge on P and the charge itself. How can you confuse this? At the point P there is no charge there. Otherwise the problem would have given to you. There are two charges, +1 and volume charge density. So when you do something, please concentrate and think. Don't multitasking, do something else. So similarly, the concept of electromagnetic field, we shall see now, also has some interaction. So the concept of force acting on a unit test charge, force. You will see now the field concept again has to do with some magnetic interaction, force, we shall see very soon. So compare those two now. The source of charges, the source of electromagnetic field, source electric charges, magnetic field, current, flow of electric charges in motion. So ask a question in the exam or in the quiz. I have a system of charges, static, they don't move. Calculate the electric field. calculate the magnetic field. Of course there is no magnetic field because the charges are not moving. If the charges are not moving, there is no current. There is no current, there is no charge. Because the source of magnetic field is the current. And the current or electric charges in motion. The charges don't move, no current, no electromagnetic field. It's a simple thing you have to remember, you have to concentrate. So for electric field we saw, we work with D. D is epsilon times E. And for magnetic field we shall see work with H, not B, H. But of course the relationship between B and H. H is the amperes per meter, B is so many Webers per meter square, the magnetic flux density. If you know H, you can find B is so big than H. Because mu naught is the property of the medium. 4 pi 10 minus 7 is given to you. This is a so-called the permeability, the magnetic property of space, free space. Similarly, epsilon naught is 8.85 10 minus 12 is the dielectric property of space, very small. Epsilon naught dielectric constant, you multiply, you get the total. Okay, so down here, as you said before, epsilon is epsilon naught, epsilon r, which you know already. Mu equal to mu naught, mu r, as usual. So epsilon naught got no units, dimensionless. Dielectric constant alumina is 9, no units. Epsilon naught. Dielectric constant of air 1, unity 1. Epsilon naught is 1 for air. For a magnet, mu r can be 1000 or 800, but for free space, no magnetism, mu r is 1. It's well known, these are all straightforward. Okay, so we shall see now, very soon now, how to calculate, how to define, how to quantify H. So we know H comes from a current, so you know. Okay. When you notice the similarity between them, analogy. D, epsilon E, B, mu naught times H. You can see the analogy between them. For a DC, for a electrostatic, for static fields, E and H are not connected, they are not connected. So let's now look at something for a while, start off something. So question is, if I have a source of current, you've already seen you have a source of charges, electric charges, I can find the electric field at a given point, any point P I can find. So the method is that set, I pretend there is a charge of +1, test charge or at the point P. Then I proceed to use Coulomb's law to calculate the force acting on the charge of +1 there. The answer give me vectorially the electric field, full stop, finish. Otherwise, what formula I'm going to use? I don't know the formula for electric field. That's why we derive this concept of force acting on unit test charge. So now question is, we know that charges are the same sign, SIGN, repel. Charges, unlike charges, different sign, attract. So now how do we know something that I took for granted but seems to be that it's all very, very fuzzy? If the charge of +Q is here, how do I know the field go this way? Away from the charge Q. But this, when you go this way, it means repulsion. I put a charge of +1 here, test charge QT of +1 here, it will repel. So the direction of repulsion of unit test charge is the indirect electric field. That's how we define the electric field. Put a charge of +1 there, calculate the force on the test charge, in magnitude direction given the field. So therefore to find the direction, we just look at it. I imagine there's a charge of +1 there, it will repel because it is positive. So if this is negative, the negative is here, minus Q, If I draw a line here, I put a charge of +1 here, it's not going to repel, it's going to attract. So the electric field will be pointing towards the positive. So this concept of unit test charge, the tests are always taken as positive. Test charge is very, very useful. Okay, so now we proceed to look at how to calculate the magnetic field coming out for a source of current, and the current assumed to be DC, direct current. And this was found by experimentally, by two Frenchmen, Mr. Biot and Mr. Savart. So they call it Biot-Savart group. Biot-Savart. 2% French, Froggy French. Okay. 1820, more than 200 years ago. But for DC, for steady current, it doesn't work for, it doesn't apply very well for time varying current, high frequency. So look carefully at this picture. The DC current flow is in this wire. And now, if you think carefully, critically, we already said before, how can it be possible? There is no closed circuit. How can the current flow? How can the current start from 0, become I, become 0 again? Strictly speaking, not correct. But of course, for the sake of illustration, I'm assuming that this is part of a circuit. This is part of a closed circuit. I pick only part of it. Okay? Otherwise, this will not satisfy continuity of current. Of course, this is part of a loop somewhere. So, at a point P, distance R, I want to find what is the magnetic field at point P here. The problem gives to me part of a wire carrying current I, the steady current I, DC current I, and the problem tells me at a given point P, distance R, in this case here, what is the field at the point P, this small element dl. I break the length of the wire into small dl. What is the field at the point P? What is the magnetic field at the point P? This is the problem. I want to field here, not there, anywhere else, I want there. So you have to be very careful what you do when you do a problem. You have to make sure you are focusing on what you're doing, not being distracted by other places where you want the field to be. So I want the field at point P. Okay. So this two persons, Savart, Biot and Biot-Savart, they did some experiment and they come out with the result. First, they found out that the direction of H here, they form like a loop like this, but on the plane of the paper here, if I grab the wire, I grab the current, I put my my thumb in the direction of current, and I twist my finger. If I twist my finger, my four fingers will go into the paper. Into the paper means I'm looking at the back side of an arrow. I have an arrow, the tip is the point, the back, the feathers is like this. So I'm looking at the back side of the arrow. So this question ask me now, when I twist my hand like this, if my finger come out like this, at this point here, suppose I want to feel at point P here, at the point Q here, when I do this, here it goes into the paper and come out here. Here the magnetic field is coming out. Because the magnetic field always in a loop, always is found in the loop, we shall see later. So at this point P, where this is the problem, what is magnetic field at the point P here? The element of magnetic field, DH, contributed by small element dl carrying a current I. Of course, small element dl, all the elements carry the same current I, continuity of current, because the DC current, the current here, all I. So the length is dl. So the longer I take dl, the stronger the field, obviously, because the contribution is more. Okay? So when I draw this like that, it means the magnetic field is going into the paper like that. If I reverse the direction of the current this way, suppose the current is going this way now, this direction. the field at point P will be going out of paper. My thumb will go this way, come this way. So this is called the right hand corkscrew rule. Pick out your right hand, if you know where your right hand is. Some people are left-handed, no? So if you are left-handed, I advise you to use the left hand and take the opposite of what you get. You get the same thing. Because opposite of left hand is right hand. I know there are some people who are left-handed. Otherwise they don't know which one is right hand and which one is left. Okay. So at the moment the direction is here. Okay. Before I go on, let me just this is the initial. Before I go on, let me show you a few so you can test yourself whether you know understand what you're doing. Suppose I consider a loop on I, say A, B, C, D. A, B, C, D. At the moment, this is I. The loop is closed, therefore it's going to be I, it's going to be I, it's going to be I, because DC current, I. So the thing I want to do now is, at the center of this loop, what is the contribution coming from AB direction? So, I grab the wire, current, thumb point direction of the current, and I twist. My four fingers come out. So therefore, this one gives rise to this. Of course, I'm looking here, coming out. I want the field at point P, center. If I want the field up here, at the point Q, different already. At the point Q, the field will be going into the blackboard. If I want the field at point P, at the point Q. Grab the current. We're talking about AB, not the rest. AB. Grab the wire current, thumb point direction of the current, and twist. I'm going into the paper. So I show the back on the arrow. So now if I look at the center now, for example, at the center, I grab the current again and twist. On the pen and the paper at the point P here, the field is coming out. Due to this one. Now, let's look at contribution due to AD, also coming out. AD. Coming out. DC, coming out. BC, coming out. So the four arms of the current contribute to some field. I'm talking about direction, not magnitude direction. The direction all the same, coming out. Okay, but if I do the same thing with a point Q outside, I want the field, what direction the field at point Q? Going into the blackboard, into the slide. If I look at the contribution due to the, let me just cover this so you don't get confused. Contribution due to DC, contribution due to DC, I grab DC. The eye is flowing down. I grab, finger for thumb this way, I grab. At that point Q, I want the field coming out. Can you see this? You better convince yourself so that you know what you're doing. Of course, you have to ask yourself the question, I must make sure I want to find the field at the point where I want it to be. I want to find the field at the point Q, not P. Different question, different problem already. At the point Q, this one gives rise to the field which is coming out, magnetic field. At the point Q, the contribution from AB is going in. So, okay, pull up your right hand and see. You can, if you do that right, you're okay. But of course, the right hand rule for fine direction of magnetic field is a very convenient way because it's very physical. But actually it's based on the vector cross product. is based on the vector cross product, which you shall see on the last thing tonight. Huh? What? You are thinking aloud again? Nothing too much, you know. So this right hand rule, you can look carefully now. Using our right hand corkscrew rule, you grab like this, at that point P now, what Bill and Sabah found out after they found out the mathematics is that it's the same as the direction of H at the point P here is given by I is the scalar, dl cross unit vector R. So dl cross R, take dl cross R, you will twist like this. The third finger go into the middle. So this is the confirmation of the corkscrew rule. So dl cross R, this vector cross product, A cross B, A cross, okay, take a driving wheel, dl cross R, and then twist the shaft of the wheel is going into the paper. Correct? So therefore you can say dl cross R vector is the same as the corkscrew rule. The corkscrew is far more convenient. Just grab and go ready. Same way. So what this about found out was this form. So if you now break this into simplification, 1/4 pi r squared, r is the distance here for a small element. I, the current flowing in this wire element. dl cross r, cross product, vector product, cross product. Therefore, it is the magnitude of I, magnitude of dl, magnitude of angle, that is sine theta. But a cross product is a vector. Therefore, this you can see the direction of dl cross r is into the paper down here. Therefore, the direction of H at this point here is 90 degrees of plane coordinate dl r, unit vector r. Okay? So as I said, check that it is corkscrew. So this, when I here we're talking about a linear element, this idea can be completed if I take the integration complete circuit in the closed path. Of course, it has to be a closed path with DC. I integrate over the whole loop. But of course, this is a generic form. Actually, this is not so simple. Just telling you what is the generic form of this answer. To get the actual answer, I have to give you the data. The very detailed data. Sometimes the current is not in a wire, the current will be in a volume, in that case, the same kind of law happens, take place, except that J cross R dV. We are not going to meet that. Yeah. Same thing. But now, before we stop tonight, what you find is that the magnetic field at the given point, due to a wire element carrying DC, there is about R squared. Inverse square law. But we shall see this is only true when the wire is of finite dimension. Finite dimension, we shall see there will be an extension later on. This a special case where your wire will be infinitely long. When wire infinitely long, we shall see is very, very simple. Before we go, let's look at this case for a wire bounded by I assume that your maths is reasonably okay. So what we're going to find out now, what is the magnetic field at point P coming out for a wire of length bounded by alpha and beta. I'm not doing the length here, the length is undefined here. This distance R, 90 degrees to this wire. So this wire is very long. This is part of the circuit. This is part of a circuit again. So the origin is here, but it is not at the center of the wire, not necessary. And a point P is found at the distance of R. In this particular case, R is taken at 90 degrees to the line here. 90 degrees for the system. Okay? From P to R here, 90 degrees, not 90 degrees here. Okay, so maybe I should call it, later we shall see R equal D, small d. Okay? So we're going to apply Gauss-Savar's law now to this wire. This wire is bounded by angle alpha and beta. But I want you to notice carefully, the angle alpha is measured with respect to the current direction. This is, I draw the bottom of where the current goes into the wire. I join the point P where I want the field to be. Nowhere else, I want the field at the point P. Not here, not there, not there. There. Call this alpha. Like this. On the extremity of the left element here, I shall draw a line from there to the center, to the point P, call this beta. Beta is measured with respect to the current. The current flowing this way, so this is beta. Beta is not here, it's there. You have to get this angle right, because this is what we're going to observe before we apply to get some result. Okay so far? So we're going to apply Gauss-Savar's law, I dl sin theta upon r squared, or I dl cross u, whatever it is. But here we already put it in the simplest form. In this case here, we can see current going this way, the field going to go inside the blackboard here. So I dl sin theta, the theta is the angle between the element dl and r, u r here. I think I better change this. So I dl sin theta upon the distance here, okay, but the distance is not r, the element is here, element is r, the distance is r cosec theta, because the small element dl we're looking here is r cosec theta. Cosec is 1 over sine, cosec is hypotenuse of the opposite, so therefore you can see this r cosec theta. This is r, this is theta, therefore this is r cosec theta. Sin theta is here. But looking at this geometry here, this is negative. Minus L is r cot theta. Cot theta is adjacent over opposite. Cot theta is minus L upon r. R is here. Better write properly. This is r cosec theta. This is r. R is taken for convenience 90 degrees to the current element. There is no harm done in this. Okay. So therefore, by differentiation, dl as a variable here, dl or dz, doesn't matter. Differential of cot is minus cosec square, minus plus, so r cosec square theta and theta. So now substitute, dh, I dl sin theta, okay, divided by 4 r cosec square theta, I substitute, my dl replaced by d theta r cosec square theta. When I do this, I get this. So therefore, the final expression for the element of magnetic field contributed by small element dl is given by I sin theta d theta over 4 by r. R disappears by r. R is here, 90 degrees today. So when I integrate now, I have to find the contribution. All this element will give me field in the same direction. You can see all will go into the paper. Therefore, I can simply integrate. When I integrate, integral of sine is minus cos. Because you differentiate cos, you get minus sine. When you integrate sine, you get minus cos, you get plus sine. So alpha beta, so therefore you have integrate, substitute I upon 2 pi r cos alpha minus cos beta. So for the short length of wire bounded by angle alpha at the bottom and beta on top, answer is 7. Now what happens when the wire is infinitely long, very, very long? When it's very, very long, the extremity here, theta goes to 0, alpha goes to 0, beta tends to 180 degrees. Pi. So now, the result is, of course, to go from here to here, do the integration from here to here, please go and do it to convince yourself. Don't accept it. Active learning, not passive learning, accept everything given to you. So when alpha tends to 0, beta tends to 100 degrees of pi, you can see cos of 0 is 1, cos 90 is minus 1, minus 1 plus 2 times. So therefore 2 and 4. So therefore its result is a beautiful result for a very, very long wire. And the distance of r from the wire, perpendicular, the magnetic field is given by I equal to pi r. That applies only to DC, steady current, like all DC now. So I say here, watch out. With this problem, make sure you get all the angles right. Here, note carefully. R is the length OP and is 90 degrees to I, taken here, this particular proof, this particular result. Alpha and beta are respect to I direction. You can see the I direction is taken as here. You take the first extremity, join the point P where you want the field to be, nowhere else. Alpha is beta. Here alpha is acute, less than 90 degrees. Beta is given by more than 90 degrees. Not always the case, of course. You shall look at one or two examples before you go on. Suppose this is the wire going here. I. Okay. Triangle, a triangular loop of current. I give you the sides, I think, as a problem. The question would be, if I ask you calculate magnetic field, and so you can complete where? Cannot do something unless you know what you want. So you want to find the field at a given point, suppose this coordinate is A0. This is 0A. Triangle is isosceles. The loop of current triangle, I calculate the field at this point. P coordinate twice A0. Using what you have discovered just now. I just want to show you the angles now, very important, how we calculate, how we get the angles right. Obviously there are 1, 2, 3 actors playing part there. There will be superposition again. So we're going to use superposition of the contribution from the side A, B, C, A, B and C, A, B, BC and A, B, BC and AC. So we shall look at the contribution A, AB, contribution AB, BC at the point P. What is HP here? That's what we want. This is the question. You are given the question, you are given the data, this is the origin, 0, 0. Now we can proceed to tackle the problem. If I don't give you the data, you cannot solve the problem. It's obvious, right? That sounds to be so obvious. The obvious is never obvious. Just like common sense is never common. This is the problem. People trying to solve a problem, they don't even give it the data, they don't even have the data. And of course, at work, you are given a project to do, no data, you jolly well go and find the information from the handbooks or whatever it is. You cannot say no data cannot solve. Okay, so we look at this problem now. We're going to find the angles first. I'm interested in the angle. So at the point P, let's do the contribution due to, say, this one first, AB. So contribution due to AB, current I in AB here. I have to look for the angles alpha and beta. So at the point P, I draw a line from the extremities to the point P. And the angle alpha is made with respect to the current, so it will be coming this way. Draw the point here this way, from this to here. Now we go to the shoes and look at this one. And 2 to the arrows here. So the direction of the extremity B to the B, let's call this B here, AB, to the point B here, 2 arrows here. So this is angle alpha. So this is alpha AB. Alpha AB given to B. I call it AB alpha B. How about the angle beta? The angle beta is a line, the current goes this way, direction. The point from the top here to the point P is here. Go the arrow again. So, the angle is beta AB. So now the next problem is for you to find the angles, to find the expression. So in this case here, the y element is here. The distance perpendicular dr here, what is r? R here is given by this distance, and then maybe 2a, sorry. The distance from here to here, a and 2a. So we finished already the first part. So the contribution from the arm AB is known already. Is that okay, anybody? Is anybody lost? Anybody not sure what we are doing? We are just using a result we have discovered with proper care about the angles we take. The angles alpha and beta will be taken first where the current goes in, element. The line drawn from the edge of the current to the point P, by double arrow here. And the current direction is here, so this is alpha. Of course, alpha is pi by 2, no problem, right? So the angle beta on top is the angle which the other point, the other extremity here, joint P, which is here, is angle beta. Now, of course, I can calculate trigonometry. Angle beta is here. This one here. This is beta. This is 180 minus beta. This is right angle triangle. This angle, I can find the octane. Octane is 2 over 1. Octane of 2. So therefore I can find. This is trigonometry. But this shows whether you have mastered all your fundamental of maths. Not maths for passing exams only. Maths to apply. So I leave it to you to do that. Let me now look at the next arm before we go. So the rest is for you to do. I'll go to the arm. Now the arm BC. The arm BC is here, current flowing this way. But I want to feel that point P here. So this seems to be a bit difficult, but if you remember, if you look at the original Besavant's law, if I do the same thing again, you find the answer will be 0. Answer will be 0 because, look at back now here, the original Biot-Savart's law at the point P. If the angle theta is 0, answer 0. Right? From Biot-Savart's law, ideal sin theta, if the angle is 0, answer 0. Let me just cross it. If the point P, the angle is 0, sin theta is 0, finish. So if the point P lies on the line of the current, angle is 0, the answer is 0. Think about it and meditate and concentrate. Continue. So therefore, the angle theta is 0. But of course, there are other ways of doing this. We can use the actual formula if we want to. So this would be like that. This is I, this is BC. Of course, you know that's 0. H, BH, P, and BC is 0. P. So this is I, this is BC. The point is here. P. So the point P lies on the current direction. So for the angle alpha, suppose the point P was here, suppose it was here, and I'm going to push it down. So here, this way, suppose the point P was a P dash first there. So it's from here, and alpha be here. This will go down here. And the beta be here. Right? Let me twist it this way. I obey this rule now. When this point P prime, P dash become P, what happens? Beta becomes 180 degrees, alpha becomes 180 degrees. So cos 180 degrees minus cos 180 degrees is 0. I hope you can see that. 180 when P prime goes down here on the point P, limiting form, because if I draw P, you cannot see. So, if you have the current element here, on the line of the current element, the field is 0. Okay with it? From this formula, or from Biot-Savart's law, sin theta originally was 0. Sin theta was 0. Where is it? The other one, just so you know. Ideal sin theta, or R squared. So whichever way you want, it's 0. Of course, I have to do this because then otherwise I cannot find anything here. I have to push it, the limit P prime becomes P. Can anybody follow this? Anybody cannot follow? Unless you're concentrating, you cannot follow because you're concentrating. Any question? So let's now look the arm AC. Last one. Arm AC is here. The point P is here. Nowhere else. Point P is there. So, again, the same style, the same thing. So from here, I draw a line here. From the edge here first, the bottom. Okay, up to P. A lot of space there. This is my alpha. And this way. So this one here, I draw a line here. This is my beta. Beta, alpha, alpha AB, alpha AC. This is C. This is, oh sorry, alpha, yeah, this is to AC. Alpha AC. Alpha AC. This one beta AC. There you go. This is trigonometry, nothing else. But of course, as in everything, you have to get it correctly. There is no probably yes, more or less, no. Either you get it right or wrong, full stop. Cannot be second guess, cannot be maybe, cannot. Not allowed. So So the rule is that you must make sure that you measure the current, the angle with the current, with the diagonal current, and the edge here, draw a vector, draw a line to the point P, and this one, draw a line to the point P, and you find the angles. And this particular case here, for C, you can find what is the R perpendicular, you can find the distance using trigonometry. So the rest, I leave it to you. This one is a harder problem. Simpler problem is in the tutorial. So just to test whether you can understand how to find the angle. So we shall stop here and continue the two.
我看，因为我是看这个啊，我是看下面那个我这是 alpha， 这个大概是下面那个是 beta， 这出来看嘛，这样我就不懂了。
So the tutorial, there's a question there on this similar thing. I think the solution worked out for you. Please go and have a look, concentrate, and see whether you understand or not.
它是这样的，它是这样，所以我按程式来，你从这边这个 angle 是alpha，它是在它的轴是这是 alpha， 这是beta。不懂哎，刚我就看他是这样讲。
我只知道那个 beta is opposite from alpha。
这个的合力是你去找啊。
我刚睡觉哎。
很累耶。
哦。觉得看书。这个是 A。拜。拜。Friday。
当成 AB the same principle apply to the electric field. You just take a point, just take a position. Then 你看你的 conductor 是在哪里 from the beginning to end. So you draw a thing, then you mark the angles.